Hello and welcome to an introduction to risk-based inspection. My name is Paul Sheriff and I'm a Chartered Engineer and a Fellow of the Institution of Mechanical Engineers. I've been working on COMA sites in the UK for over 25 years. I'm API 580 certified and I've been implementing risk-based inspection since 2012. Risk-based inspection was first introduced in the early 1990s and is still being adopted as best practice worldwide. It helps asset-intensive companies to understand how their plants are aging, and when it's implemented, it can satisfy the regulators that the company is using effective mechanical integrity management processes to help prevent major accidents and to minimise loss of containment incidents. During the next 20 minutes, I'll be covering some of these topics during my presentation. What is risk-based inspection, or RBI? How should you go about preparing for an RBI project? Why conducting a damage mechanism review is so important, how to calculate risk and the risk ranking process, and finally I'll cover the kind of benefits that you'll see through implementing a risk-based inspection project. So why implement risk-based inspection? Well, traditionally the inspection of pressure vessels and pressure systems were completed on a time basis, with little consideration of the equipment age, its duty or operational damage. Advances in inspection techniques and standards such as APIs 510, 570, 653 and some of the newer standards have led to a more condition-based approach, use of half-life intervals and on-stream inspections instead of internal inspections where rates of low have become more common. We are now much more aware of the effects of ageing, and the codes and standards allow plans to be more flexible based on the results of a risk-based inspection assessment. These changes have led to the development of the next generation of inspection, risk-based inspection. This approach is fundamentally based on information collected in order to assess the risk of a loss of containment event occurring, and essential to the process is a risk analysis to understand the likelihood of failure due to damage, deterioration or degradation, and an assessment of the consequences of a failure. The objective of any risk-based inspection process is to maintain the mechanical integrity of pressure equipment and to minimise the risk of loss of containment due to deterioration. It can be applied to pressure vessels, process piping, storage tanks, pressure relief devices, heat exchangers, as well as boilers and heaters, and the pressure containing components of rotating equipment. It's important to bear in mind that although this concept is applied by the inspection and engineering personnel, it needs the commitment and cooperation of everyone associated with operations to succeed. The output of an RBI assessment should be an inspection plan, and the plan should include the following 6 items. What is driving risk? For example, is it the consequences of failure? The inspection methods that should be used? Is that visual inspection or UT going to be used? The extent of the inspection. Are we going to inspect the whole of the vessel or just specific parts, for instance? The inspection interval, which is usually in months or years. Any risk mitigation activities, such as painting or replacement of nozzles. And finally, the residual level of risk after the implementation and the mitigation activities have been implemented should be assessed. So what do we mean by risk? Well, the very simple mathematical definition of risk is as follows. Risk is probability times consequence. A better definition is that risk is the combination of the probability of some event occurring during a particular time period and the consequences, which are usually negative, associated with that event. The risk being calculated by RBI is relative risk, not absolute risk. Absolute risk is time-consuming, costly and difficult to accurately calculate. We're looking to determine relative risk so we can quickly rank the risks. In risk-based inspection, we're looking to calculate the risk of a specific consequence, like a pinhole leak or a rupture for instance, and then combine it with the probability of the specific consequence occurring. An important part of the RBI journey is to establish what level of risk is acceptable for the organisation. In any project, scope is extremely important, and an RBI implementation project is no different. The scope of an RBI implementation project can be established by resolving these 4 questions. Firstly, what is the objective of the RBI project? What are we hoping to achieve? Are we looking to better understand risk on site, or to better use our resources, for instance? Secondly, we need to identify the physical boundaries of the project. What's in scope and what's out? Are we going to consider the whole site? A unit, for instance, or just specific vessels? Thirdly, we need to identify the operating boundaries. What operating period are we going to examine? Is it the full life of the unit? Will we include startup, shutdowns, upset conditions, for instance? Lastly, we need to consider how will the assessment be carried out. Assessment methods range from qualitative through semi-quantitative to quantitative, and I'll explain more about this shortly. The implementation of a risk-based inspection programme is still a project. As with any other project, a project plan with timescales should be developed. The progress of the project should be reported on a periodic basis, and key performance indicators should be used to measure progress. In that way, roadblocks or issues can be identified and resolved quickly. Next, I want to cover the roles within the RBI Implementation Project. Any RBI project needs a team approach because no one has all the information to execute RBI on their own. The committed team needs to have access to all of the following roles, and to avoid confusion, the roles should be formally recorded. You need a team leader to form the team. You'll need equipment inspectors or inspection specialists to help gather information on the condition and history of the equipment. A corrosion specialist is required to assess the damage mechanisms, their applicability and their severity. A process specialist is very useful for information about process conditions. Operations and maintenance personnel are needed to verify that the equipment is being operated in line with the operating windows. Management is required to provide sponsorship and resources. A risk analyst is required to carry out the risk-based inspection analysis. Environmental and safety personnel, they'll provide data on EHS regulations. And lastly, financial personnel will provide cost data on the financial impact of equipment shutdowns, for instance. Not all of these roles are full-time, and indeed some of them can be done by the same person. It's not uncommon, for instance, that the risk analyst role will also be completed by the team leader. Less resources are needed once the programme is established. As I've stated before, there are different assessment approaches. So which approach suits the project? Would you choose a qualitative approach, a semi-quantitative approach, or a quantitative approach? Well, the approach taken very much depends on the risk that is anticipated, as well as other things like time constraints, the availability of data, and the availability of resources. For low risk equipment, a simple qualitative approach might be adequate. It would use engineering judgment, a little bit of data, and it can be completed relatively quickly. For high risk equipment, a more detailed quantitative approach may be more appropriate. It is data intensive and it will take longer to pull together, but it will give a more discrimination between equipment risk. The semi-quantitative approach has both the advantage of the speed of the qualitative approach with the rigour of the quantitative approach. This simplified block diagram shows 6 essential elements of inspection planning, and this approach is applicable regardless of the RBI approach that is taken. The slide shows a diagram which is taken straight from API 580. Good examples of sources of data are things like P&ID drawings, inspector reports, maintenance records, corrosion studies, management of change records and equipment data sheets. And all of this information should be validated before it is used. Using the information, it should then be possible to calculate consequence of failure and probability of failure. And this information can then be used to calculate risk during the risk assessment process. Next up, risk ranking is used to present risk results in a format that is easy to be communicated, like a risk matrix or a risk plot. An inspection plan is the next step, and that can be created now we understand what is driving risk. The plan should include damage mechanism, techniques, the coverage and the interval of the inspection. Some mitigation can be achieved by inspection, however there are other methods, repairs and replacements for instance. Consequence of failure can be reduced by modifying the process. Probability of failure can be improved by using better materials of construction. Improving isolation procedures will reduce detection and isolation times, and the use of blast-proof buildings, for instance, will improve consequence of failure. Lastly, reassessment should be carried out whenever an inspection has been completed or significant changes have taken place. like process changes for instance. The RBI team shall consult with a corrosion specialist to define equipment damage mechanisms and potential failure modes. Examples of damage mechanisms are things like corrosion, cracking or metallurgical damage. Damage mechanisms can affect equipment both externally and internally. Having identified the damage mechanisms, it should be possible to define potential failure modes. Failure modes are kind of what they say really. They define how the component will fail. Will it rupture? Will it show leakage or fracture? All of the assumptions about design pressure, temperature and materials should be noted. And all the process conditions, including startups, abnormal conditions and things like that, should also be considered. The results need to be tabulated as shown in these examples. So for instance, external corrosion leads to localised thinning, leading to a pinhole leak. Internal cracking leads to small cracking through to through cracks or even rupture. During the damage mechanism review, it is vital to establish the integrity operating windows of the process. Integrity operating windows are sets of limits used to determine the different operating variables like temperature, pressure or concentration that could affect the integrity and reliability of a process unit. Put simply, IOWs are the limits under which equipment or a process unit can be operated without serious damage. If the equipment is operated outside of its IOWs, at too high a temperature or too low a pressure for example, for a predetermined period of time, then preventable damage or failure may be caused by higher corrosion rates or another damage mechanism. Now we understand how the equipment will fail, it is possible to assess the probability of failure. Probability of failure is typically expressed in terms of frequency, usually frequencies per year. Probability of failure is determined by understanding two processes. Firstly, damage mechanisms and their damage rates, and secondly, the effectiveness of the inspection programme to identify and monitor the damage mechanisms. Using a qualitative approach, the probability of failure can be assessed using engineering judgment. It could be categorised as high, medium or low, or on a scale of 1 to 5. Using a quantitative approach, it should be possible to calculate damage rates and evaluate the effectiveness of the inspection regime. Whichever approach is taken, it needs to be documented and validated so it can be repeated. Now we understand how the equipment might fail, it should be possible to estimate the consequence of the failure. Usual consequences are things like health and safety impacts, such as the release of a toxic cloud, environmental impacts, such as the loss of containment into a waterway, or economic impacts, like the shutdown of operations to effect repairs. It should be stressed that the worst possible consequence is not always the most likely. Consequence of failure can be expressed in different ways, like injury severity, affected area, or cost. And using a qualitative approach, consequence of failure can be assessed using expert knowledge and experience. Consequence of failure using a qualitative approach could be categorised as high, medium or low, or on a scale of A to E. Using a quantitative approach, it should be more possible to calculate the volume of fluid released and the effect it has on people, property, the environment or the business. As before, with probability of failure, whichever approach is taken, it needs to be documented and validated so it can be repeated. The next step is calculating risk and risk ranking. The risk of each specific consequence can be calculated using the probability of failure and the consequence of failure values that have already been assessed or calculated. Now we're talking about risk being the probability of a specific consequence times the effects of that specific consequence. It's usual to represent these results in a risk matrix, like a 5x5 matrix shown below, or a risk plot. In the risk matrix shown, high risk equipment is shown in red, medium risk equipment is shown in yellow, and low risk equipment is shown in green. Once the risk values have been plotted, the evaluation process can begin. Equipment can be ranked or prioritised according to risk. The risk matrix is also a good tool to show whether the risk is acceptable or unacceptable. And the use of the risk matrix also shows whether consequence or probability is driving the risk. For risks that are unacceptable, mitigation measures should be considered. For instance, you could decommission equipment. So is the equipment really necessary for operations? You could inspect and make repairs? So can you, for instance, implement a cost-effective inspection programme with repairs? Can consequence of failure mitigation be implemented? As an example, can consequence of failure be reduced by design changes, for instance to the isolation or detection systems? And fourthly, can probability of failure be mitigated? So for instance, can materials of construction be changed to reduce corrosion rates or to eradicate a damage mechanism? Now we can create some inspection plans. Inspection on its own does not reduce risk, but the information gained by an inspection can better quantify the risk. Inspection provides information by identifying, monitoring and measuring damage mechanisms. Some damage mechanisms can change too fast for inspection to be effective, or another damage mechanism can be triggered. This is where integrity operating windows need to be identified. We discussed those before. Where risk is driven by probability of failure in particular, there is potential to manage risk through inspection. As I've stated before, an inspection activity should be developed which considers the following factors: the frequency of the inspection, the coverage or areas of equipment that should be inspected, the tools and techniques required to be cost effective, and lastly, the procedures and practices to ensure that these techniques are executed effectively with qualified people. The final step is the reassessment step. Risk is dynamic. It changes with time. And results from an RBI assessment need to be updated by qualified personnel. An RBI reassessment should be carried out whenever changes occur. These changes could be things such as after significant changes, so after process conditions have changed or damage mechanism rates have changed significantly. After a set period of time, there are set default time periods in the API codes, for instance. After an inspection, where we've got new information available to help update the assessment. After implementing a risk mitigation strategy to help determine its effectiveness. And before or after maintenance inspection downtime, which is commonly known as a turnaround, to focus on high-risk equipment, to determine the new risk levels and to highlight the difference that the turnaround has made. The results from all these assessments should be used to determine future inspection plans, no matter how low the risk is. And all of the RBI procedures that we've used should be captured in a documented management system to help sustain the RBI programme. I now want to talk about some of the benefits of implementing RBI. The obvious benefits of implementing RBI are as follows. Firstly, it improves the management and compliance of health and safety on site. RBI very much complements the other areas of risk management, and I'm going to be talking about more of that on the next slide. It brings consistency to the inspection department through better procedures. It promotes teamwork and interaction, because as we've talked about, RBI is very much a team effort. It promotes better knowledge about risk throughout the organisation. Secondly, RBI enables the inspection department to identify and repair deteriorating equipment in a timely manner. This approach gives a far better understanding of risk of the equipment. It gives us more knowledge about the equipment and the process, especially after a damage mechanism review has been completed. It will produce an overall reduction in risk for equipment that's been assessed. It also enables maintenance inspection activities to be prioritised. And it's a continuous improvement tool. Thirdly, it produces cost savings, although the extent of those cost savings will very much depend on the thoroughness of the previous inspection regime. It produces cost savings by identifying and implementing cost-effective inspection strategies, and also identifying equipment that does not need assessing as frequently. So how does it complement other process safety activities? Well, a better understanding of risk can complement the following activities: the PHA process, or the HAZOP process for instance, because it gives you a better understanding of how the equipment might fail. A LARP, as we've talked about, it's a continuous improvement tool. It can also help the site major accident prevention policy through its focus on detection and isolation procedures. And it also will complement the COMA report. RBI can be used to assess changes during the management of change process. And it can also be used to start discussions about risk, and in particular, what is acceptable risk for the organisation. If you put all this focus on prevention of failures, then overall it should reduce adverse incidents on the site. In summary, I hope that you now have a better understanding of risk and a better understanding of risk-based inspection. We've shown you a roadmap of RBI implementation, and we've talked about the important stages of the implementation. Finally, we've seen the benefits that can be realised by implementing a risk-based inspection programme. I hope that you've enjoyed the presentation, and thank you for your time.